And we took a look at, as the Earth is cooling, it kept shrinking, the crust cooled first, and as everything began to shrink, it began to shatter. At one time, the entire planet had a very smooth, quartz-like shell to it. It was actually a granite and quartz mixture. And the entire planet was wrapped in granite and quartz, which cooled on the surface. That began to break up, and you'll find granite, well, you have two kinds of mountains. You have the upheaval mountains, and then you have the volcanic mountains. Well, the upheavals are where plates are turned up, they're heaved up on end, and you'll find those all over the world. A lot of them in Europe. Europe has a lot of granite. But you find a lot here, a lot of granite out in Arizona, and most of the granite in the schist and all that is actually dated back to Precambrian times, just like we're saying. It was the first formed hard crust, which was then broken. As the plates began to shrink, one plate would move under another. They shrink and then they expand depending on what the heat's doing at the time, global warming, you know. So one plate will find its way under the other plate and push it up into a mountain. And you can tell those because they're like steep on one side and then slowly graded down on the other. If you have a mountain that's like steep and sloped down, it means that your intruding plate is coming in this direction under it and pushing this up. It's that simple. We have a lot of that up here. A good place to study that is the Copper Country, which is right down the road from us. You have a plate there. It's one of the Lake Superior plates, which was intruded by, I believe they call it the Buffalo Plate or whatever. It comes from the east, and it went under the western Lake Superior Plate, and it pushed up the land just like this. And as it did that, it opened up a fissure from down below, which had all of the greenstone. The last greenstone flow came up from that fissure and created these domes on top of the mountains. I believe we're the first people to identify the Greenland doming effect. All the other knuckleheads down at the geology department think that the greenstone flow, which is, by the way, the world's largest single flow of magma, they say, well, that's all the greenstone flow came way back when 400 different layers of copper and in your greenstone and different layers. There were like 400 layers that were laid down from volcanics in that area. They said that's when all the greenstone came up. No, it didn't. We saw evidence of something else going on up at the central mine. We went up the hill, and right there you could see rocks as big as a room in your house, literally shoved up and broken off with sharp edges and everything. These are like really, really dense iron rock. And all around the hill you saw these rocks just pushed up and kind of shoved aside. That's when I heard a voice. God told me, go up to the top of the hill, you will find a greenstone piston or dome right at the top of the hill that pushed up through straight up. Well, if it pushed straight up, doesn't mean that it was back in the time of the main greenstone flow, because that's been pushed up on an angle by the Buffalo Plate. So we walked up there with our grandkids, and sure enough, top spot on the top of the hill towards the middle, the highest point was a greenstone dome of lava, just pure lava, and it came straight up, which means that happened after the plates were tipped up. And those plates were like 400 layers, different layers. You had sandstone, and you had amygdaloid, what they call amygdaloid, which are ores. And then you had, of course, the greenstone. And a lot of those amygdaloids, you had conglomerates. Some of those are in there. But the amygdaloid actually carried a certain percentage of copper. It was like 2 to 4%. But it's enough copper at 2 to 4% to crush and extract it and make a good profit on at only 2 to 4%. Anyway, we studied the copper mining up here for years and years and years. We went out and found old mines. We actually found trenches and pits dug more than 10,000 years ago. They may have dated back 50,000 years ago when you add Europeans coming over here, the Vikings coming over here and digging 500 million pounds of copper to feed the Bronze Age of Europe, because they didn't have that much copper there. It was all taken out of mostly Isle Royal, and there were some other mines on the Keweenaw Peninsula. So that's where most of your early copper came from, is right down the road here. Like we said, it was the first and biggest metallic mining industry in the world, and it really supplied the vast amount of copper that they were using back in the 1800s, 1900s, until some of the mines like in Montana and Arizona, places like that, they found copper ore, which was actually a copper compound, and they processed that into copper and actually surpassed the Lake Superior production, because they did a lot of open pit mining out there, which they didn't do here. Can't open pit mine here. Anyway, so back to the origins of gold. We saw how you have two kinds of mountains. You have this upturned plate type, and then you have another type, which is your volcanic. Your volcanic is basically something like that. This is your iron plug up here. Actually, this land used to surround it. It was pushed up, and then it eroded down and created this sloping side like that. You have another mountain. It's called a pluton. These are more like rounded hills. You have a plutonic mass of magma sitting under it. That's an intrusive. This is extrusive. And you have something else going on here, which is your ridgeback. That's where you see like a ridgeback of usually basalt. It's basalt degrading down into hematite. And you'll sometimes have feeder veins coming off of that, but going up to this ridgeback of usually basalt. You'll see it. It's jagged magma at the top. It's basically magma. This is from a crack, one main crack with minor cracks coming off the two sides. This is just a huge piston coming up. And a lot of these you'll see out there. I'll show you in the future. A lot of them they actually still have their craters. You see these jagged craters, a jagged crater rim. I'll show you some pictures of that later on. But those are all your mountain types. Now, all of your volcanic types, your intrusive, extrusive, all of these have magma coming up from the core. Most of them are either basalt, or you'll see them at this stage, they're red iron oxide. Not all of them have gold in them, but most of them do. They have some percentage of gold. Now, a lot of people say, this guy doesn't know what he's talking about. We see gold in the quartz. It's into quartz. No, it was exchanged or secondary enriched into the quartz. Quartz does not have gold in it underground. Those two layers do not meet underground. Quartz is not an igneous rock. bang, bang, boom, broke a lot of old doctrines and theories, but quartz is not an igneous rock. It's metamorphic. It's not only metamorphic, it's also a fluxing agent, like we explained earlier. When welding rod is manufactured, particularly with MIG wire welders, they have to put about 8 or 9% silicon dioxide or sand in it because it's a fluxing agent and helps the metal to flow smoothly. Well, that's what quartz does. Quartz actually acts as a flux. You find a lot of quartz like in your granites and stuff like that. Granite acts as a fluxing agent too. A lot of minerals act as fluxing agents, even calcium carbide, different crystals of calcium, or any of them. They're all fluxing agents to one degree or another, which means they draw the gold out of something else. They make the gold flow easily from somewhere to somewhere. Now, like we explained before, hot iron, sometimes there's nickel in it, but the hot iron comes up, it hits that layer, that globe layer of gold, melts it down, draws it up towards the surface as that chimney of iron is coming up. And when that chimney of iron comes up, if there's a clear path to the surface, the gold continues up and it becomes an iron plug or an iron chute, an ore chute. And a lot of times you'll find these pure, they call them red dirt chutes. You'll find them surfacing. It's pure iron oxide, but you'll see a lot of gold coming out of that iron oxide because nothing stopped that chute from getting to the surface. The gold came up in the iron. It's just that that was iron which had not mixed with other compounds like manganese oxide, or any of your steel additives, your metal additives. Basalt is not pure iron. It's got a lot of manganese oxide in it, giving it that dark color. A lot of different compounds in it, which explains why there are two kinds of black sand. You have a black sand which is non-magnetic. You have a black sand which is magnetic. The non-magnetic black sand is manganese dioxide. The magnetic black sand is actually broken down basalt iron. Basalt has a high iron content. So some black sands will react to a magnet, some won't. That's why you can find gold attached to certain black sands and not others, because the gold isn't in the manganese dioxide, it's in the basalt. It comes up in the basalt. You'll find, we'll show you in the future, we'll show you pictures and things as we get into identifying where to get gold. You'll find certain dikes coming up. You got country rock, and this dike will come up in this area. This dike is a magma flow, usually dark basalt. We're running right along the edge here. If you have something like granite running along the edge, where the two of them contact, you'll get a contact enrichment. Now, some people think that the gold is coming out of the granite towards the basalt. As the basalt comes up in a molten state, it heats up the granite and pulls the gold out of the granite. Well, that can't possibly be true. When you look along the edge here, the contact zone, you'll find these individual rocks of debris. Now, these are metamorphic. They've been metamorphized. They're usually a dark red, some black in it, but usually dark red iron oxide and the gold is in them. Well, that's because as this basalt came in contact with the granite, the minerals in the granite acted as a fluxing agent, drawing the gold out of the basalt and into this region where they contact, and actually created or metamorphized the basalt into an iron oxide form, which then drops the gold out of it. But the gold is not coming up in the granite. The granite has no gold in it. It's coming up in the basalt. The granite draws it out. Now, people say, oh, we've seen all these quartz stringers in granite around the Catherine mine and all that, all these fantastic quartz stringers and the gold's in them. Yeah. But that's quartz coming up after it's been acted upon by hot iron, either basalt or just plain iron. It's exchanged the gold, and the gold comes up in the quartz into all those micro cracks and fissures through the granite. It's not in the granite. The granite is broken up, it's shattered, and it's the quartz filling that's bringing gold up from the iron underneath. So the conclusion that we're coming to is that, number one, you got to take a fresh look at the origins of gold, where it's been deposited on the earth, how it's coming up. Then you'll develop an eye for identifying the new places you can go to find the new deposits. There are many deposits that have never even been discovered. People have walked over them for hundreds of years, thousands of years. They don't even know it's there. We're going to show you new methods of how to determine where that old gold is. The old gold is the good gold because it hasn't been touched by anybody. Nobody's gone in and picked it clean. If you're going to go on trying to get gold out of gullies and washes and stuff like that, you'll get a little out from year to year after the rains, fine. But you're still only looking at 1/10 of an ounce per ton of material that you move. And unless you've got the right kind of machinery, the right kind of tools to move a lot of tons, you're going to have to move at least 10 tons of material every week. And I'll tell you, you can't do that by hand. You won't last long. If you have a machine, I know what kind of machine you need, but we're not going to get into that now. That's a development way down the line. I know what it is, but I don't want to touch that. What I want to identify or show everybody how to identify is where the old gold is at that nobody's seen before, and that means new tools. It's new tools to identify deposits. It's new tools to identify exactly where your big deposits are, how deep they are underground, and we have tools like that already. And some of the tools we're developing right now show you how to go down 3 or 4 feet and find pockets of gold down there. Anyway, we'll get into that in the next section. Next section will be about how to identify where the gold deposits are today. And it's pretty fundamental, it's pretty simple, but you're going to have a whole fresh new approach and a new look at where it's at and how to get it. So we'll leave that for next time. And remember, my name is not Jeff. I am not Roger from Oz. I'm Ken from Copperland. And like I'll always tell you, gold turbine products that we're designing and building will transform you magically. From a 90-pound gold panning weakling into a beast of a miner. Now, if you want to be a beast of a miner, you want to get that gold, stay tuned. I'm going to show you how to get it.